Today we're going to look at simple circuits and some of the basic concepts behind them. So let's say we take a battery. Let's go ahead and draw out a battery here. Now the way a battery essentially works is creates a separation of charge. So on one side of the battery we're going to have excess electrons, and on the other side of the battery we're going to have excess protons. And you probably learned about this in chemistry. Using two metals and some kind of solution in between them to separate them out. So anyways, these electrons, they are all trying to repel each other. So you have lots of negatives trying to repel, but they have nowhere to go. So let's imagine we take a wire here. Okay, we'll start our wire. And the wire is the conductor. So this is essentially going to give us a path for the electrons to move. So as soon as we connect the wire, all these negatives now have a path to go. So they're going to start getting pushed. Electrons are trying to repel. They're going to start being pushed through the wire here. Now the wire itself has electrons. So there's electrons here, everywhere, right? Well, at the same time that these are pushing these electrons this way, the positive is attracting the electrons this way. So you have a push, you have a pull, and the electrons are going to start flowing. In fact, all the electrons in the wire are going to start flowing simultaneously. So it's not like there's this push, like a domino effect, where they kind of work their way through. It's more like all at once, everything's going to move. Everything's going to start moving together, all the electrons in our circuit. Now the battery is what we call a voltage source. This is what provides the energy and the push through the circuit. The flow of electrons here we call a current, similar to like a water current, where instead of water flowing we have these charges or electrons flowing through our circuit. So here's another visual. In this one, again, here's our battery right here. Here's our wire. Now notice the wires themselves, we have our open switch, have electrons in them, but they're not moving. You might think, oh, how come these electrons don't just push electrons here? Well, they might do that, but then you're going to get a bunch of electrons piling up over here, and they're just going to push back. Or likewise, maybe this pulls electrons, but then you're going to have all these positives left here, and they're going to pull back. So that never happens when our circuit's open. Now when we close it, as soon as we make the connection and we give a path, now all the electrons are going to flow through. And again, this is a simultaneous thing. This simultaneously pulls, this simultaneously pushes, and then all the electrons through the whole circuit are going to move together. So let's start defining some terms. The first term is voltage, and essentially this is, it's also called an electric potential. This is what provides the energy to the circuit. So it's the push. We're going to be pushing the current through the circuit, pushing the electrons through the circuit. The units are going to be volts, and what a volt is, it's 1 joule per coulomb. So what it does is it gives energy to each coulomb of charge. 1 volt would be giving 1 joule of energy to each coulomb of charge. A lot of times we use the analogy with water. So for example, if you have a water pump, this would be the voltage similar to your battery, and the water pump's going to be pushing the water through your pipes, similarly as a battery might do. Another analogy would be like with gravity. So if you think of a voltage as increasing energy, so a battery might raise up the charges to a higher energy level, and then as they flow through the circuit, they're going from higher energy to low energy, and this would be from one end of the battery down to the opposite end of the battery. You'll often see this called EMF and electromotive force. So again, you can see this term, this force, where you're pushing these electrons through the circuit. Current is the next term, and I've used this several times. There's kind of two ways we'll refer to current. So as we've been talking, current is going to be the flow of electrons. Remember, electrons are small, they're far away from the nucleus, so they're easily movable. So what's actually flowing in the circuit are going to be electrons. So we'll refer to this as true current or electron current. There's another term which is referred to as conventional current, and this is the convention. So the convention of current that was made way back when used positive charge. This was before they actually knew what was flowing, and they just assumed it was positive. So unfortunately, they never changed to what's actually happened, and we've just kind of stuck with conventional current. So for example, if you look at this picture, the actual electron flow would go from negative end to the positive end. However, the conventional current would be if the protons or positives were flowing, and that's going to be from positive to negative. So whenever I refer to current, I'm going to be using conventional current. So if I ask you to draw the current, for example, you should draw from positive to negative. But just in the back of your mind, kind of know, oh, in real life, it's actually electrons going from negative to positive. The equation, so current is charge, flow of charge, right? Well, if we want to measure this, we're going to see how much charge flows per time. So the amount of charge per time, or coulombs per second, is what's going to be referred to as our current. So if you have more charge flowing in a second, that would be a greater current. We nickname this an ampere or amps, and that's the unit that we'll be using for current. So the last major device of a simple circuit is what's called a resistor. And the resistor, well, just like it sounds, it resists the current. So imagine right here, you have something with a bunch of atoms in it. And the electrons are not just going to flow easily from one end to the other. As they're flowing, they're going to start bumping into these electrons, or bumping into atoms and electrons, both, as they try to make their way through the atom. And so it's not going to be a nice straight path. It might be kind of this curved path of bouncing back and forth as they try to make their way through the circuit. Examples of this, light bulb. So you've seen a few pictures already of light bulbs, motors, heaters. These are all considered resistors in our circuit. So let's look at the physical characteristics of a resistor and the factors that affect it. There are essentially three main factors that affect it. The first one is what we call resistivity. And the resistivity of the circuit is going to, well, it's based on what it's made out of. So copper, silver, aluminum, silicon, whatever it's made out of. So if we increase the resistivity in our circuit, so take a look at the picture, it's like there's more atoms here, more electrons that are going to get in the way. And as the resistivity goes up, then the resistance is going to also increase. And that means, you know, as electrons are trying to make their way through, they're going to have more collisions, and it's going to increase the overall resistance. The other factor is the length. If we increase the length of our circuit, of our resistor, so here, notice if our resistor is short, it's going to be pretty easy for an electron to make its way from one end to the other. But if we increase the length, there's more things that it's going to collide with on its way, and it's going to have more trouble making its way, and so the resistance is going to increase in that case. Lastly is the cross-sectional area, so it'd be the area of this circle here. And if we increase the area, notice what happens. Well, now it's almost like there's more spacing for the electrons to make their way through. And since there's more spacing, notice if we constrict it really small, okay, they're kind of forced through this small area, and there's going to be a lot more collisions on its way through. And so the resistance is going to be very high in that case. So if you didn't write anything down during that time, here's a few things for you to write. Again, the equation here is going to be resistance is equal to rho, which looks like a little Greek P. This is called resistivity. It's based on the substance itself. L is going to be the length of it. Okay, so there's a short length, here's a long length, and A is a cross-sectional area. Big area, small area. The units that we're going to use for resistance are ohms. One last factor, temperature is also a factor. If you look at this slide, the higher the temperature, the greater the resistance. So I'll just leave it as a thought problem for you to think about why that might be, why increasing temperature would also increase resistance. Alright, so we're now going to get into the most important equation of this unit, which is called Ohm's Law. And Ohm's Law basically relates the voltage, the current, and the resistance together. So I want to see if you can derive this. Let's just do it conceptually. So for example, here's my current reading here, here's my volt reading here. If I increase my voltage, so we're going to increase the push, predict what's going to happen. So we increase the voltage, increase the push, and notice that the flow of current is increasing. And you can see that down here as well. So increasing the voltage increases the current. What about resistance? What should happen if we increase resistance? Well, if we increase resistance, think about it first, predict. Increasing resistance, notice what happens is the flow starts to decrease. And it's moving a little bit slower here, and you can see that also on the current reading here. Or if we go in the opposite direction, if we decrease the resistance, notice that the flow increases, that electrons go faster, more of them go through, and you can see that the current increases as well. So can you derive the equation then? In other words, I want you to say I equals something. Give you a few minutes, seconds. I equals V over R. Did you get that? So again, the concept is, we'll go the other way, if we decrease voltage, then the current also decreases. And if we increase resistance, okay, more get in the way, then the current decreases. Now we're going to look at power. Recall from first semester that power essentially is work over time, or more specifically, how quickly you can change energy. So it's going to be the change in energy over time. Remember the units, the base unit would be like the joule per second, so how much energy you change per second. And we kind of nickname this the watt. Well, notice that word watt, we use that in electricity all the time, right? That's probably the only place maybe in your life that you've heard the term watt. So let's recall a couple other terms. Voltage is the joule per coulomb, and current is a coulomb per second. So could you use some dimensional analysis to derive the power equation for electricity? I'll give you a few seconds. Push pause. So did you get this? Power equals voltage times current. Notice that voltage is a joule per coulomb, and current is a coulomb per second. And when you multiply the two, you get a joule per second, which is watt or power. So again, power is the rate of change in energy. And with electricity, oftentimes it's going to be the change from electrical energy to thermal energy. So let's go back to the simulation. One of the last things I want you to notice is this down here. It's telling us the temperature of our resistor. And notice these atoms are moving. The atoms in the resistor are moving. And the faster they move, if you recall, the faster atoms move, this is going to be a higher temperature and has more thermal energy. So notice we said power equals current times voltage, or voltage times current. So if we increase our voltage, each electron is going to have more joules per electron, right, per coulomb. So if we increase that, it's going to hit them harder, and they're going to start to move faster. And if you notice, the temperature rose down here because it's hitting them harder. We can also change the current, and to do that on the simulation, I'm going to change the resistance. Recall, if we lower the resistance, we should increase the current. So if we lower the resistance here, we're going to increase the current. They're going to start hitting the atoms even faster, harder, and the atoms are going to be moving really, really fast, and that translates to a very hot temperature. On the other hand, if we increase the resistance, which is going to slow down the current, now it's going to hit them. They're not going to vibrate as violently here. That's going to be a cooler temperature. And if we decrease the voltage even more so they're barely even moving, and that would be a really cold temperature here. So the last thing we're going to look at are the circuit symbols. You probably noticed in the lab you did that it was kind of a pain to draw out little light bulbs and batteries all the time. So we have a way of simplifying our drawings. So these are some of the common circuit symbols that you'll see. So a wire is just going to be a line. A resistor is going to be kind of squigglies that resist. A light bulb, there's several ones. One is just simple an X, a circle with an X. I actually like to draw a light bulb with a resistor and a circle. So you'll see me do that a lot. That's also going to be a light bulb. A cell would just be like a single cell. It has a line. This is a voltage source. This is the positive end. Just remember the larger line is the positive end. This is the shorter end. And then a battery is just multiple cells. And so again, the larger line represents the positive end, and the negative end is the shorter line. And remember, we'll always be drawing conventional current, which goes from positive to negative. Switch just looks like this, an open. This would be an open switch before the circuit works. If you push it down this way, you're going to close the switch. Some other symbols that we see, one is a V with a circle. This is called a voltmeter. This is what's used to measure voltage. And A with the circle is called an ammeter, and this is used to measure current. And the last one you'll see a lot, it looks like this, a little squiggly, not a lot, but we'll see it from time to time. And this is what we call a fuse. And we'll talk about fuses in a future lesson. So these are the common symbols that you will be using for this unit. So for example, if I wanted to draw a circuit, a real simple circuit, it might look like this, with a switch, a resistor. Okay, this would be the positive end of our battery, this would be the negative end of our battery, this would be our switch. And then once we close the switch, if I ask you to draw the current, you would draw it from positive to negative.